So, hello. In this podcast, we will be talking about mostly regular expressions. Why am I doing a podcast on regular expressions? Is because during the lecture, I feel we didn't spend enough time on regular expressions, and I don't want to be confused about regular expressions. So I want to help you out with that, and so spend a little bit more time talking about them. So, during the lecture, I defined, I introduced you to regular expressions and then I showed you how it is possible to map from regular expressions to regular languages using the inductive definition of regular expressions, right? Um, I want to go the other way around. So I want to show you that regular expressions are just a shorthand for regular languages, right? It's just a shorthand for notation. How am I doing to do that? Well, first of all, let's talk about operations on regular languages. So I showed you that it is possible to do the union of regular languages, of sets. I showed you sets and I showed you that regular languages as sets, right? Languages as sets. So A union B, you can do that. A concatenation B, you know that and you know how to do that and you can do that. A star, so the clean star of a set, you know how to do that. Well, turns out that, okay, imagine the set of all regular languages. So you have a collection, and inside this collection, you put all the existing regular languages, right? This set is said to be closed under some operations, some under union, concatenation, and clean star. What does this mean? It means that if you take two elements from this set, so if you take two regular languages and you do the union, what you get as a result is a regular language. If you take two regular languages, so two elements from this set, and you do the concatenation, you get a regular language. If you do the clean star, you get a regular language. So you don't move from the set of regular languages, you stay inside. That's why this set is said to be closed under union, concatenation, and clean star. Okay? So I'll just write this down. Closed. Just closed. So this set is closed, right? I'll just write, these are closure properties. So it's clear properties. Okay. So this is nice because it gives us a way of building regular languages. Actually, it gives us a way also to define regular languages, right? Why is that? Because we can do the induction trick I showed you during the lecture while defining regular expressions, okay? And so, for example, we can say, let's talk about languages defined on some alphabet sigma, which is, I don't know, the set of symbols which are A, B, C, D. Okay? So languages defined on this sigma here, okay? Let's do the inductive trick, okay? So we know all finite sets of strings are regular. We know that strings with one symbol are strings. So we define four regular languages starting from the symbols in our alphabet, right? So we just do this. We create a set. We create sets containing one element each of the starting alphabet. This, of course, you can do with whatever alphabet you can come up with, right? I'm just doing an example with sigma here. So you create this A, B, C, D. Well, these A, B, C, D sets are all regular because they're finite. They contain symbols, or you can say they contain strings of length 1 if you want. Okay, so they're regular. This means that you can do the union of them, you can do the concatenation of them, you can do the clean star of them, and still produce regular languages. Actually, you can produce all regular languages defined on sigma by using the union, the concatenation, and the clean star on these elements here. Okay, so for example, I can do the A union B and get AB, for example, right? This is another regular language. I can concatenate this with D, for example, and create another regular language. What's this regular language? We saw concatenation, right? This is equal to, you get one element from the first and then one element of the second. In the second set, we have only one element, so we get, we do only one concatenation. Then you get another element of the first set and you concatenate it with one element, and you see this is the resulting set AB ADBD. Okay, so this is another regular language. Okay, now to obtain infinite regular languages, you use the clean star. Okay, and this is interesting. The only way you can introduce infinity in regular languages is thanks to the clean star, which is defined as an infinite union of sets, right? This is an interesting thing to think about. So you cannot just, well, it doesn't matter. So ADBD is a regular language. For example, I'm just doing examples, so you can do the union of whatever you want here and get another regular language. You can do the concatenation and get another regular language. You can do the clean star of this, for example, ADBD clean start, and get first of all the empty string, right? Then AD, then BD, so all sequences of length 1, then all sequences of length 2, AD, 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 BD, BD, AD, BD, BD, then all sequences of length 3. I won't do all of them. So, and again, this thing here is a regular language. And actually, so as I told you, you can get all regular languages defined on sigma by by just doing applying these operations on these elementary set of elements. Sorry, these elementary components. Okay. So this fact here, this nice little fact, we will use it to show how regular expressions are just shorthand for this, for operations on regular languages, getting you in return other regular languages. So let's talk about the union. Well, for example, this A union B, we will write it down as a regular expression as A plus B. Okay, this symbol here stays for the union. We're losing the brackets, we don't need them, so this is shorthand. Okay, it's a way to write this down using less symbols, making using a clearer notation. So A plus B. Other people would use A or B. This is the logical OR, this pipe here, or maybe A union B. Some people, I just use plus. Okay, so this A plus B is equal to A B. Okay, so this is the union. What about the concatenation? Where let's represent these as a regular expression. So the set AB concatenated with set containing just D. So we know that AB is we can write it down like this. and then we have to concatenate with D. And here I introduce another piece of notation, which is just the parenthesis, just to make sure it's clear that I'm concatenating this D to this object here, not to B, but to this object here inside the parenthesis. So again, we're losing the brackets, okay, and we're expressing everything in terms of the elementary components of these regular languages, right? So the actual symbols. Okay, so a plus b d is equal to this thing here. This is the concatenation, and here it is. So what about so this clean star thing again? So this, if you remember, we grabbed this thing here from here. So this is the a b concatenated with d clean start. Okay, so this is a plus b d, and we do the clean star. Okay, so this is all of it, really. So what you're doing with regular expressions, you're just mimicking this structure here. Okay, the fact that you can obtain regular languages by doing the union of these elementary components and doing the concatenation and doing the clean star. Okay, and you are just using a different notation for that. Okay, and the nice thing is that, of course, because you can produce all regular languages on sigma by using this inductive fact here, you can equally express all regular languages on sigma with regular expressions, which is pretty nice, right? Okay, so that concludes the definition part of things. I didn't really define much, and just wanted to show you another take, another way to see regular expressions, another way to build your intuition of them, so you understand them better and you are more comfortable working with them. So now for a little bit of exercises. So all of our exercises will be defined on the alphabet sigma A, B, C, D. Okay. Okay, let's start. Let's work out some exercises so you can see what procedure I use, what's the way I apply these definitions. So language of all strings on sigma ending in D. What does this mean? It means that before D we can have whatever we want, okay, whatever string we fancy. The important thing is that at the end of that you find a D. So how to express this in regular expressions? Well, remember that this means all possible strings on sigma, right? The way to write it down in regular expression notation, so expressing it as a composition in a way of these elementary elements, these symbols, it's like this. Then you end up with a D. So this means all possible strings defined on the alphabet sigma, and then a D. The important thing is at the end of these strings you find a D, and then you're happy. Okay, so just to make sure you understand, what is this? Well, this is epsilon. Now I'm using set notation to to show you what this object is. So A, B, C, D, of course, so all sequences of length 1, then all sequences of length 2, C, A, D, etc., 3, 4, etc. Okay, this is that, and then we concatenate a D. Set notation, I will do something like that. Okay, this is what I'm doing under the hood, let's say, of regular expressions. Okay, so strings on sigma containing BBC. Well, what does this mean? That BBC is not in a specific position inside the string, but it could be anywhere. So we could have something before or maybe not, and we could have something after or maybe not. But the important thing is that somewhere in between you have BBC. So BBC, something in before, something after, maybe, maybe not. So you can have whatever string you want before or after. Of course, we put the clean star to show, to say there are all possible strings. Oh, this is a C. Okay, and this is it really. So you could have anything before, anything after, maybe nothing, because of course here this means also the empty string. Okay, you have the empty string because of the clean star, and that's it. Okay, so let's go further. Strings starting with an odd number of ACs ending in B, or strings of length 1. This is more complex, just to show you, the possibilities of regular expressions. So, starting with an odd number of ACs and ending in B. So, an odd number of ACs. So, there must be one. Okay, and then it's odd. So, I will say AC, AC, clean start. This means you could have nothing. So you have only one AC and it's okay because it's odd. Or you can have AC, AC, and then it's good because you have this one, you add the other two, and you get an odd number. You can have AC, 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 which is okay because again this is even, plus 1 it is odd, and you see where this is going, right? So you just repeat the thing inside the parenthesis. You see where this is going. So cancel this. So starting with an odd number of ACs ending in B. So you could have really anything. Again, here we could have a problem though. Yeah, here we have a problem. Why? Because if I do now what I wanted to do initially, and I didn't think about it, but it's good that I made this mistake so I can show you. So I wanted to do this and then B, right? But here we have a problem. What problem is it? That so I would have said that here we can have whatever string we want, but this is actually false, because if we have another AC somewhere, then we mess this up, because now we have an even number of ACs. You see what I mean? That's a problem. Now, of course, it is possible to use regular expressions to say, okay, anything but AC. So this, no, but all the rest, yes. It is possible to do that. But as it turns out, it is actually quite a lengthy process. In fact, you first need to create an NFA accepting your language. Then you can convert that down to a generalized NFA, that's what it's called. And then after that, you can extract, let's say, your regular expression. Okay, but I won't explain any of that today. I don't want to, kill your precious brains. So I will just modify this exercise so that we don't have to deal with that. Instead of ending with in B, let's say that it is followed by B. Okay, so this is much easier. We just say this. Okay, so string starting with an odd number of ACs, we have this followed by B. Okay, and then we can have anything here, right? So the important thing is that you have an odd number of ACs and then it is followed by a B, and then the string can continue, it doesn't matter. Or So the other kind of strings in this language are strings of length 1. So all of these, or A or B or C or D. You see, why is that? So this plus here means or, right? It's an alternative operation. So either the strings will be in this form or they will be in this form. So this is what the plus is about. This is, I think, the first time you see the plus outside parentheses and outside, you know, this form here. So this is just a or. Sorry, no, an or. So now strings where each symbol is separated by two A's. For example, here B, AA, B, AA, C, AA, A, AA, D. It's like a waltzer. So how to do this? Let's see. So it's separated by two A. So you can have whatever you want here, A, B, C, D. Well, whatever symbol you want, not whatever string, because it has to be separated with A's, right? So, and then you have two A's. Is that right? I think it is. And then, so it is separated by A's. Oh, sorry. But I see that they don't end in A. So what I will do is clean star this. So it means that you have a symbol, then you have AA, then you have maybe another symbol, and then you have AA. You see? So what does it mean, this clean star here? Well, if you first do this, you realize the strings you end up with are A, AA, B, AA, C, AA, D, AA, right? Then you clean star this. What you get is A, AA, for example. Well, first you always have the empty string. Then you have A, AA. Then you have B, AA, C, AA, D, AA. Then you have all sequences with two elements. So AA, AAA, AAA. You see this? So just to make sure you understand their sequences of two elements. A, AA, B, AA, etc, etc. Okay, you see where this is going, I hope. So I'll just delete this. This is what you get in the end. So we clean start it, and of course if we leave it like this is wrong, because it will end in AA, or maybe an empty string. So this is wrong. We want it to be right, and we add concatenation here. A plus B plus C plus D. So with all, so you have all this AA separation, and in the end you get a symbol exactly like, you know, the example string here. Okay. So string containing at least one B. Well, let's add something. Containing at least one B. It's not interesting. String containing at least one B, or strings made of A's. Okay, so for example, how to do this? String containing at least one B. So it can be anything. A plus B plus C plus D. So you can have anything before, then you have to have a D, and then you can have anything late after that, A plus B plus C plus D. Again, or strings made of A's. So you have this, your strings could be of this form, or you can have all strings made of A's, so something like that. Okay, so this is, what is this? Again, epsilon, A, blah, 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 blah. Okay. So hopefully this should clarify regular expressions to you. Hopefully. But the only way to get everything right is of course to just do exercises. And yeah, I mean, I can explain everything twice or thrice or 4 times, but in the end, what will decide, how well you will go about your exam is how much exercises you will do. Okay, and there's no escape from that in mathematics. The only way you can memorize these things is by doing them. So this is it for regular expressions and exercises. Well, bye bye.